Hello everyone, and welcome back to another video from the Mathnasium. We're going to do a really short little unit here on exponential functions. And to illustrate what an exponential function is, I'm going to talk about a couple different scenarios. First of which, my good friend Peter here. Peter is in love. And Peter, on average, when him and his love procreate, are going to make around, let's say, 8 offspring, and Peter and his true love are also can do this every month and a half or so. So Peter, these rabbits can go crazy, right? Rabbits can reproduce faster than you'd think. They go fast. So here we go. They can create many offspring very, very, very quickly. And so what I'm going to do today is we're going to talk about kind of what that looks like actually. And this is very loosely, I'm oversimplifying it, but let's say if they can produce like 8 rabbits, then that would be, let's say that's 4 breeding pairs that are produced from that point, right? So let's say each of those pairs then produces. So after 1 generation, you have, 4 rabbits. After 2 generations, you're going to have 16 pairs of breeding rabbits, and so on and so forth. So as these generations continue, the number of rabbits that there are is growing very, very quickly. It's not increasing the same amount each time. So the first, the first iteration, or rather, the first generation, there were 4 rabbits. Then there were 16, and then in the next one, if we continued drawing these little fingers coming off of our tree, this would be 64 breeding pairs of rabbits. Well, that's a crazy amount. Things are growing very, very fast. This is not linear growth like what we've seen previously in the class. Like when we talked about the water fountain and in the hallway, and we can see the number of water bottles that are filtered. People are drinking about the same amount of water every single month. So that number is probably staying roughly the same as time continues. However, as time goes on and these rabbits reproduce, if they're left to their own devices with no predators or anything to keep their population numbers down, then these rabbits there can be too many of them quickly. And why is that bad? Well, that can, potentially cause a problem with their food source, and they could all die. A great example of this is Adak. Adak Island is on the Aleutian chain here in Alaska. It's way, way out there, and there used to be a military base out there. The buildings are still there, but somebody brought caribou out there many, many years ago, and there are a ton of them. And you can fly on Alaska Airlines. You can go out there, and the limit is 5 per person. You can go out there, I think, double check your regs, but you can go out there and you can go crazy and get a ton of caribou, because Fish and Wildlife, they know that, or Fish and Game knows that they don't want that population to get too big. It's better to harvest and give an incentive for people to go and harvest caribou than it is to let the population get too large, because then they would eat the entire food supply. There's no predators out there, and they'd all die off. So exponential growth is something that you really need to have a good handle on when you're talking about population growth, and also something very relevant, like the spread of the coronavirus that we're currently going through. So I'm going to give you a couple examples of where you see things growing exponentially. The number of water bottles that system out there fills, that's not exponential. It's increasing roughly the same amount, each week or each month that passes. The amount that it increases changes. It gets bigger and bigger and bigger. So here are some examples of common exponential growth that you might see or you might hear about commonly in discussion. Okay, so population growth. Population growth without some sort of incentive or some sort of factor that's controlling that growth will grow exponentially. The spread of disease also will grow exponentially if not controlled. That's why we're given these rules to wear our masks during the coronavirus. We're trying to make sure we're not spreading it at as great of a rate as it could if it goes uncontested, right? The growth of your finances. If you have money that is sitting in a bank and you are earning interest on the money, pretty soon you begin earning interest on the interest that you had. And so your growth, your savings, does not grow linearly. Your savings grows exponentially. Now, it's not a steep exponential curve. It's not like rabbits reproducing, for example, but it does grow exponentially. It can be modeled best by that. And the last one is radioactive decay. There are unstable atoms, certain radioactive material, and those unstable atoms start losing subatomic particles, and you can measure that, and people use that to find the age of certain items or certain fossils or just historic artifacts. So, and that's through, like carbon dating and other methods that are similar. And I'm not an expert in that by any means, but we used radioactive decay to make and do those calculations. Okay, great. So here I have a couple slides of the start of the pandemic, and you can see this data is clearly nonlinear. It starts off gradually and then picks up and picks up and picks up, and just spreads and spreads like crazy. This can be modeled by, it's best modeled by an exponential model. So we're going to see what that is and how it works here in just a minute. It spreads just like so here we are, the U.S. Thought we were doing a good job at the start of the pandemic, and turns out we weren't doing that good of a job. Other countries seem to have maybe gotten a grip. Some of them are a little smaller, but anyways, it starts taking off, and yeah, you can see this curve as it's taking off. It's not growing linearly. At least the United States one is not at the start. Everybody starts as a curve. Okay, so how do we graph these, and what do they look like? So an exponential equation or an exponential function is going to look like basically y equals, and then you have some number b to the power x. So our horizontal, our independent variable is actually an exponent in this case. So let's take a look at our first example, and we're going to graph this. I'm going to go over the strategies for graphing it. Since I don't know what this looks like yet, I'm going to go through and kind of do it the hard way, which is kind of the plug and chug method, and then I'm going to show you an easier method by which you can graph these after I do the first two. So I'll do the first two examples kind of the hard way, and then we'll go through and go from there and kind of make some adjustments. So the best method I would recommend for graphing these is I always start by plugging in, we're basically just picking x values, and we're going to find the y value, and we're going to get a set of points. We're going to plot those points, and then we're going to connect them with a kind of a smooth curve. So I always start by plugging in x equals 0. That's usually my starting point, because 0 is typically very easy for us to do math with. So when x equals 0, y is equal to 2 to the 0, which is 1. So we get this point 0, 1. Well, that was easy. This point is part of my function. All right, and I like to start at 0, and then I like to work my way to the right, and I like to see how it's changing. If it looks like it's taking off, I'll just go very slowly. If it's gradual, I might space my points out a little bit. All right, so here we go. X equals 1. We're going to plug that in and see what happens. Y equals 2 to the, I'm replacing x with 1, 2 to the first, which is 2. And you end up with 1, 2. Hey, that's not too bad. I can manage this. And how about x equals 2? What's going to happen here? We get y equals 2 to the second, which is 4. So we get the point 2, 4. So you might notice, as I'm going to the right, I'm just adding a new number to the power of 2. So it's 2 to the 0, 2 to the first, 2 to the second. So at 2, 4. So when I go to 3, that's just going to be 2 to the third, which is 8. So you can kind of see the pattern as you're going to the right. Great. Okay, now I start working into my negative numbers here, so I can kind of see what this looks like. X equals -1. So that's going to be y equals 2 to the -1. Remember, a negative exponent means it's going to move down to the bottom of the fraction. I might divide these up a little bit. Okay, so that just turns into 1/2, so we get the point -1, 1/2. So I'm going to go -1 up 1/2. Fantastic. And I'll continue this process. to the left. Going this way, x equals -2. That's going to be y equals 2 to the -2, which is negative exponent goes on the bottom. 1 on the top, which is 1 over 4. So we get the point, -2 comma 1 over 4. So think about these as a decimal, if that's helpful for you. -2 comma 1 divided by 4, which is 0.25. So I'm going to come over here, and what we get is we can see this kind of curve forming. It looks like it's coming down closer and closer and closer. Now, so here I have our y value. When it was 1, our y value was 2. When it was -1, it was 1 over 2. When this is our x value is 2, our y value is 4, and when our x value was -2, it was 1 over 4. You can kind of see the reciprocal of these values showing. So if this is over 3 up 8, this is probably going to be 1/8, which is very, very close. And you're probably saying, well, when is it ever going to cross that x-axis? It's a great question. Turns out it isn't. If you plug in x equals, let's say, -6, we plug this in, that's 2 to the -6, which is 1 over 2 to the 6th, which is 1 over 64, which is very, very small. It doesn't matter how negative we make x. So if we make x super positive, it's just going to keep growing and growing and growing. If we make x super negative, it keeps getting really, really small, and as x becomes really, really, really large, as x becomes, really large and negative, so very large negative number, basically you're going to get a number that looks like 1 divided a negative huge number like this. And it doesn't matter how big this is, this will never, it'll always be greater than 0. That's not a negative number. You just get a huge number in the denominator. Okay, it doesn't matter how big this number is, it's always going to end up being greater than 0. So what you end up here with is, this is a has a name. This curve is getting closer and closer to this line, y equals 0, or the x-axis. And when you have a line that gets that is being approached like this, this is called an asymptote. An asymptote is a line or curve that is approached. But not reached. It's a very loose definition, but it'll work. So it's getting closer and closer and closer. So now I'm going to try and draw my curve out here. So it's starting here, it's like basically on the, oh, why is this dashed? Don't do this to me. Let me try that again. I got wrecked. And I'm actually going to do a different color. So it's continuing ever, getting closer and closer to 0, and then as I work my way this way, it's coming up. So basically what's going on here is when you have a negative power on the 2, that determines the number of 2's that are in the denominator. So we end up here with this 1 over 2 squared. This is 1 over 2 to the first. This is 1. This is 2 to the first, and this is 2 to the second, our y value. So as you continue this way, the power of 2 increases. If you continue this way, the power of 2 decreases. So basically, the quick way to graph these is to figure out what your y-intercept is here, where it crosses, and then anytime you go 1 in this direction, you just times by 2, and anytime you go 1 in this direction, you simply divide by 2, and you'll be able to get it really quickly. So let's kind of start from scratch here. You plug in x equals 0, and you get the y value 1, so 2 times 1 is 2, times 2 is 4, times 2 is 8. When you go to the left, divided by 2 is 1/2, half of a half is a quarter, half of a quarter is an eighth, so on and so forth. Quick way to graph these equations. Okay, how about this one in red? This one is a little bit different. I'm going to do something similar here, and this is going to behave much differently than you may expect, or it's going to look a little bit different than the last one did. So again, I'm going to do a similar process. I'm going to start with x equals 0. When x equals 0, or sorry, we don't have to write it that way. It's in function notation. So we can just say f of 0. F of 0 is equal to 4, and then we'll do 1/2 to the 0. Well, that 0 is only on the 1/2, so this is really 4 times 1, which is 4. So we get the point 0, 4. Hooray! Look at that, 0, 4. All right, let's go over a little bit. Let's do f of 1 now. Let's do the same thing that I was doing before. That's going to be 4 times 1/2, and I'm going to zoom in so we get a better shot. 4 times 1/2 to the first. Okay, well that's just 4 over 1 times 1/2. Anything to the first power is itself. 4 over 1 times 1 over 2, which is 4 over 2, which is 2. So we get the point 1, 2. So I'll go over to 1, 2. Look at that. All right, and then we can do it again. F of 2 is equal to 4 times 1/2 squared. What is 1/2 squared? Well, that's 1 over 2 times 1 over 2, multiply across the top, multiply across the bottom, 1 over 4, so this turns into 4 over 1 times 1 over 4, which is 4 over 4, which is 1. So this is the point 2, 1. There's 2, 1. This is 1, 2. This is 0, 4. Process continues. So 2, 1 is also on my graph. Okay, let's go back the other direction. How about f of -1? F of -1 is going to be 4 times 1/2 to the -1. Whoa, that's crazy. All right, there's a couple ways that you can think about 1/2 to the -1. You can think about this way, it works just fine for me, as 4 divided by 1/2. So you take the thing with the negative exponent and move it down to the denominator, which means we have a number divided by a fraction. So we use that skip, change, flip, or multiply by the reciprocal. So 4, skip, change division to multiplication, multiply by the reciprocal of 1/2, which is 2 over 1, which gives us the value 8. Or you could just do 4 divided by 0.5 in the calculator to get that value. All right, so that gives us this point, -1, 8. Okay, so let's take a look. -1, 8. Let's take a look. Let's use that same method that I was talking about before, that quick method. I do want to see this work. I want to see you plugging some stuff in. I want to see a calculation for one on the positive side, one on the negative side, and the one for 0. But basically what you can do is start at 0 and then use that pattern. Whatever is being raised to the x power, that is what tells us, this is kind of our growth factor, that tells us how we're growing or shrinking as we're going to the right or the left. So we multiply by 2 going this way, since it's being raised to the x power, and you divide by 2 going this way. It turns out the same works with this. If we start here at 4, we plugged in 0, and we start here at 4, when you're going this direction, we're timesing by 1/2, and when we go this direction, we're dividing by 1/2. Don't believe me? Start at the y value 4. Again, I calculated that from f of 0, or plugging in 0 for x. That goes to 1 times 4 is 4. And then you can go 4 times 0.5. 4 times 0.5 gives us a 2. Hey, look at that. So it drops down to 2. Times 0.5. What is half of 2? It's 1. What's half of 1? I'll do these in a different color since we did not calculate them. Half of 1 is 1/2, so this process will continue. Half of 1/2 is a quarter. It continues going. Okay, and going this direction, you're dividing by 1/2. Dividing by 1/2 is the same as multiplying by 2, but that's okay. So if I go over 1, if I'm at 8, that's going to go all the way up to like 16, which is like up here, right? So we're going to get this curve that's coming down this direction. Now this looks very different from it looks fairly different from the one that we had before. So this one is coming down this way. It still has an asymptote at x equals 0. Okay, but it looks fairly, it's different because as we're going to the right, it's coming down. This one is going up. It's getting really, really large as you go to the right. This one is coming down and getting really, really close to 0, really, really small. This, basically, when you have the thing that's being raised to the x power, this, our growth factor or decay factor, this determines whether or not it's exponential growth or decay. Since this is a fraction, since it's less than 1, this ends up being exponential decay. Okay, this is exponential decay. As we're going to the right, that's getting smaller and smaller and smaller. This one is bigger than 1, the thing that's being raised to the x power. So this is exponential growth. Okay, so yeah, it all determines, or it's all based off of what is being raised to the x power. It's bigger than 1, that's exponential growth. Ignoring the 4, it doesn't make a difference because it has the power 1. This is the thing that's determining whether it's growth or decay. It's 1/2, less than 1, so it's exponential decay. All right, we're going to come back to this. Let's do a quick summary here. So all of these equations are basically going to look like this. They're going to have some starting value a, and that basically is the value of our function at x equals 0. So f of 0 is our starting value a. And you can see that because if you plug in 0 for x, even in this general case, y equals a times b to the 0, well, b to the 0 is always going to be 1, right? Doesn't matter. That's going to go to 1, and you just end up with a. So if you have a number that's being multiplied out front here, that is going to be kind of our starting value of our graph. So if you take a look here, we have, we'll come back to this one. If you take a look here, we had 4. It's basically our y-intercept, all right? So that's where it's crossing the y-axis. That's our starting value, or our y-intercept. Okay, and then here we didn't have 1, but we could just as simply write 1 times 2 to the x, and that would give us our starting value. Or to find the starting value, just plug in x equals 0. And when I say starting value, I really mean it's our y-intercept for the exponential function, okay? Now this thing over here is called the growth factor, the thing that's being raised to the x power, or the decay factor, and I kind of mentioned that before. It is a growth factor if b is greater than 1, and it is a decay factor if b is less than 1, but should be greater than 0, should not be negative. B is greater than 0. Okay, growth factor, decay factor. So let's take a look at a couple of these. Are these exponential growth or decay? So we have 0.5 times 1.3 to the x. Well, 1.3 is bigger than 1, so this is going to be, over time, is going to be exponential growth. Okay, although there is no number being multiplied out front, we just have something to the power x. That something is less than 1, so this is exponential decay. Now, I'm going to graph this first the easy way, so I can show you the quick way to do it, and then I'll go through and justify it with some work. All right, let me change to green. Okay, in green, this is our starting value, or if I plug in f of 0, right, that's going to be 1 times 2, so I can go to 2, and then every time I go to the right, I take my growth factor and I multiply by that growth factor. Every time I go to the left, I divide by that growth factor. If I'm starting at 2, I go over 1, I'm going to times by 3, which is 6, and then times by 3 again. Oh my gosh, that's way off my graph. So I'm going to maybe do a little work to get where that would be in between those two values, so we can kind of see how that's growing. So if I did plug it in, it would end up being at 18. 18 is probably like way up here, so I can put that dot on there if I want, but I don't have to. Now I'm going to divide by 3. 2 divided by 3 is 2/3. 2/3 divided by 3 is something. 2/9, which is 0.2 repeating. Yeah. Really small. So this is exponential growth, right? It's getting big very, very fast. So it's going to come through like this. So when you guys are graphing your graphs, try and have around 5 points graphed if you can. your y-intercept, and then also like try and do 2 points on either side. Notice I can't get my second point here. So what I could do is I could come through and say, well, what about between 1 and 2? What's f of 1.5? You can plug in values that are decimals. That's just fine. Times 3 to the 1.5 power. So I can come down here, and I got to do the exponent first according to PEMDAS. So that'll be 3 to the 1.5. So this is 2 times 5.196, which is approximately 10.4. So 10, when I'm at 2, or 1.5 rather, which is right here, I'm up at 10.4, so it looks like my graph is pretty accurate. Okay, and you can go through and you can check these values if you want. You could plug f equals 0 in, 2 times 3 to the 0, which is 2 times 1, which is 2. Hey, look, that's the point 0, 2 that we just graphed, so on and so forth. And here I have my asymptote coming across. Hope that was helpful. That's it for this video. Thanks for watching. There's going to be more from the Mathnasium very soon.